Topic 16.1 is looking at what's called a rate expression. And it's going to be split into two videos, rate law and rate mechanism. So we're going to look at the rate law first. So rate of a reaction is proportional to the change in the reaction, which is delta, and then the concentration brackets is the way you can shorthand it. And that alpha is the sign for proportional, so you can shorthand your notes as well. So reaction rate equals K, which is a constant, times the concentration of your compound. And that compound is going to be the reactants that are in your reaction. So generally, just looking at a general equation, if we have reactant A reacting with reactant B, we're going to get a set of products. So what would the rate expression look like? Well, rate is going to equal K times the concentration of A to the power of M times the concentration of B to the power of N. This right here is the rate expression or rate law. So K is the rate constant. This number is specific to every reaction, therefore it has to be calculated with every reaction. However, the value for that reaction will only change if temperature changes. And we're going to look at that relationship in 16.2 specifically with activation energy. But to take away, it is specific to each reaction. A and B with the brackets are the constant concentration of the reactants in the reaction. M and N are order with respect to A and B. So what is order then? Order is an expression of the relationships between each reactant and its rate in that reaction. And so you look at how much effect does that reactant have on the reaction's ability to move forward, and it looks at that relationship. Overall order is the sum of the individual orders, and we will look at that with specific reactions. And this is going to be determined through rate mechanisms, which is the second video for 16.1. And so it all comes together. So we're learning how to use the rate law to determine order, but order truly comes from a rate mechanism. It cannot be determined from mole ratios from the reaction. It has to be done experimentally. And so I cannot drive this home. It cannot be determined from mole ratios. From the stoichiometric equation, it does not come from there. And so we have to have data there to support determining what the order of a reaction is. Once K and the orders are known, you are able to determine the rate for any reaction and go on from there. All right, so we have an example. If we have 2 H2 gas plus 2 NO gas, that makes 2 H2O and N2 gas. So this reaction is shown to be second order with respect to NO and first order with respect to H2. Give the rate equation for this reaction and its overall order. So we know rate equals K. And if you notice, this is a lowercase k because a capital K is Kelvin for temperature. And why they're using the same value, I don't know. Or sorry, the same letter, I don't know. But lowercase k is what we're looking at here. All right, so rate equals K, and so we have the concentration of H2. And I'm going to reread the problem. It is first order with respect to H2. So you can just write the concentration of H2. You can put a 1 if you want. does not matter, but you will not see it represented with a 1. And second order with respect to NO. So I want to show you here real quickly. Yes, that squared function for NO matches the order function, right? But if you look at H2 in the stoichiometric equation, there's 2 H2, but there's only 1 in the rate expression. So here we are showing you that the balanced stoichiometric equation does not necessarily determine what that order would look like. And then what is overall order? Well, 1 plus 2 are the individual orders, which means our overall order for this reaction is a 3. So now units of K vary depending on the overall order of a reaction. So we have different orders we could look at. We have 0 order. So that means the value of rate equals K, because 0 order, if you take anything to the exponent of 0, that value is 0. Therefore, the units of rate equal K. If you're a first order reaction or reactant, rate equals K times the concentration of that one reactant, because there can only be one reactant present. If it's a second order reaction, rate equals K times the reactant squared, or rate equals K times the concentration of A times the concentration of B, because those would both be second order reactions. And the third order reaction equals rate equals K times the concentration of A cubed, or rate equals K times the concentration of A squared times the concentration of B, or you could reverse that. Or it could be rate equals K times the concentration of A times the concentration of B times the concentration of C, for those very rare 3 reactant equations. But you kind of get the point. All right, so K equals the units of rate. It's just manipulating the equation over the units of concentration to their order. Okay, so to show you, we know rate from 6.1 is moles per decimeter cubed per second. And keep in mind that moles per decimeter cubed is the unit for concentration, and it's rate because we added time. All right, so for a 0 order, and that means the reactants have no effect, right? That means K equals the rate. So rate equals moles per decimeter cubed per second. And that would be the value of K for a 0 order reaction. All right, for a first order, it gets a little bit more difficult. And I'm going to run out of space, so I'm going to just write where I can. All right, so for a first order, rate equals the units of rate, so moles per decimeter cubed per second, over the units of the concentration, moles per decimeter cubed, right? And the order is 1. There's only 1 there. So when we go through, cancel out commonalities just like any other mathematical relationship, right? And we're left with what the first order equation is: rate equals seconds to the -1. So there's your first order. Okay, looking at second order, rate equals moles per decimeter cubed per second over moles per decimeter cubed, and because it's a second order reaction, we have to square it. So this gets a little bit trickier. Okay, so we need to cross out commonalities. Well, we have moles per moles per decimeter cubed. Got a little happy there. All right, so we cross out the commonality. So moles per decimeter cubed takes out one of those moles per decimeter cubed for the order. So what does this leave us? Rate equals moles to the -1 because it's on the bottom. That decimeters becomes just a regular cubed times seconds to the -1. So there's your unit for a second order reaction. Third order. Rate equals moles per decimeter cubed per second over the concentration, moles per decimeter cubed, right? So cross out the commonalities, moles per decimeter cubed, you're only taking one of those, right? So that means rate equals moles -2, decimeter to the 6th per second. And there is the units for your third order. So if you just remember what the units of rate are and the units of concentration, and you know the overall order, you can figure this out mathematically. So you don't have to have this memorized. So don't stress about that. Just follow the same mathematical concepts you guys have known for years. So K can be calculated from a rate expression if we know everything, right? So we have to know the concentration of the reactants, 1, 2, 3, all of them, right? And we have to know the rate for each of those reactants within the reaction itself. Now, keep in mind, the only thing that can affect the value of T is that the value of K. The value of K will increase only with temperature. It will not increase if you change concentrations of the reactants. So K is consistent for a reaction no matter the concentration of the reactants. It's only when you change the temperature of that reaction does K change. All right, again, we will touch that back on that in 16.2. All right, so here we have a calculation. If we have just a general expression, right? Rate equals K A squared times the concentration of B. Okay? So calculate the value of K, including units, for the reaction when given the concentrations of both A and B are, so concentrations of A and B are 2.50 times 10 to the -2 moles per decimeter cubed. The reaction rate is 7.75 times 10 to the -5 moles per decimeter cubed per second. What is the value of K? Well, plug it in. So we have 7.75 times 10 to the -5 equals K times the concentration of 2.50 times 10 to the -2 times 2.50 times 10 to the -2, or you could have just squared the first one, right? Okay, so remember up here, I did not write this well. A is a second order reaction, so we need to make sure that A has a squared function on it. Okay, so manipulate it so that we have K, and so 7.75 times 10 to the -5 divided by 2.50 times 10 to the -2 cubed, essentially, and you're going to get 4.96. And so it's a cubed function. This is a third order reaction. Therefore, it becomes moles -2, decimeter 6, seconds -1. And there is our answer. Now, one of the things that could be given to you is a graph. And so interpreting how to interpret a reaction based off a graph and its order. So we're going to look at a concentration versus time graph. All right, you're going to see my wonderful drawings. So we make our graph. Here we have time. Here we have concentration. Okay, so if we have what's called a zero order reaction, rate equals K. So that means you're going to have a constant rate as you decrease your concentration of reactants, because the whole point of reactions and rates of reactions is looking at how fast your reactants are disappearing and or how fast your products are appearing. Rate law only deals with the disappearance of your reactants. Therefore, we always are going to have a negative or line. So a zero order is constant. Okay? Then a first order reaction, rate equals K times the concentration of A. So rate decreases with concentration. And it's a relatively constant graph. And so if we, that was not very good, I apologize, but so there's a first order reaction. And then a second order reaction, we have K equals concentration of A squared, or concentration of A times concentration of B. It's steeper than the first order and levels off a lot more. So you have a much higher decrease and then it levels off significantly more over time. Now, the problem with a concentration graph for a first and second order reaction, okay? It is actually very difficult to determine, and it's unclear if it's a first or second order reaction. So concentration over time does not give us first order and second order clearly. It can be interpreted, but it can be very difficult. So what we will use a rate versus time graph. So draw my graph again. And so remember, rate is something we would calculate and then graph. So our x-axis is time, our y-axis is rate. So a zero order reactant has no change in rate, right? Because it does not affect the reaction. So it is a zero zero rate, right? A first order reaction has a direct relationship between rate and concentration. So this is a lot easier to see and interpret. So if it's a constant rate over time, and rate's always positive, remember, so even though we drew an inverse or a negative line on the previous graph, rate's always positive. Therefore, we will show a positive slope. So there's our first order. And then our second order reaction is an exponential relationship, or it has a square function. All right, so this one is much easier to interpret. So it looks like a J-curve. All right, and so using a rate graph gives us a lot more information and detail about the order of the reaction overall. So here's something we do with the graphs, and something that chemistry we're not touching on heavily, but it's really big in nuclear chemistry, and it's looking at half-lives. So you guys have discussed half-lives before, especially in earth science with radioactive carbon dating. You can look at it with medicine and the use of iodine and barium and radioactive isotopes in medicine. Well, what's nice is first-order reactions have a constant half-life. Well, let's refresh what a half-life is. A half-life is the time it takes for a reactant to half its concentration, regardless of the starting concentration. And so that mathematical relationship is T to the 1/2. All right? Now what's nice is we can use to establish a first order reaction. So we can use half-life on a graph, and we can use it on a concentration graph, the one that's really difficult to determine if it belongs to a first or second order reaction. If we can look at the half-life And so the time in which it takes for the concentration to half itself, we could identify if it's a first order or a second order reaction, which is really cool. So here's a graph. And so if we have the concentration of iodine, right? And so here we're at full concentration. Remember, this is your initial concentration, so initial rate. And if we go down, and here we have half the concentration. And following that dotted line, it takes 8 days. Have that concentration, we're now at a quarter of the original, right? And if we see how long it takes 16 days. So that means you have a constant decrease with constant time. 1/8 takes it out, and it takes 24 days. So again, half-life, half the concentration in the same amount of time. It's a constant. Then if we look at the 16th, it goes out to 32 days. And so you can see that the distance here is equal on the y-axis, and the distance between the dots are equal. And so we can see that it's a concentration graph, right? It's a concentration graph. So we can tell that this is a first order reaction because it has the it has that constant half-life. So it's pretty cool. Last part of this video is looking at calculating the order of a reaction. So how do we go through and figure out order from data? And that's what we're going to be doing. So we use what's called the initial rates method. What you're going to do is you're going to run multiple experiments, changing the concentration of one reactant at a time, and holding the other reactant constant, so that you're not looking at two variables at one time. And then you're going to compare the initial rate of reaction to deduce the order of the reaction. Now, depending on what your results tell you, mathematically, you could determine the order of each reactant and therefore the overall order of the reaction. If you change the concentration and there's no effect on the rate, that means the order is 0. If you change the concentration and it has a proportional change, you have a first order reaction. So if you double the concentration, you double the rate. If you triple the concentration, you triple the rate. It is proportional. If you change the concentration and it has a squared effect, that is a second order reactant. So you double concentration, you quadruple the rate, right? You triple the concentration, you ninth the rate. You 4 times the concentration, you 16 times the rate, so on and so forth. So it has that squared effect to it. What does this look like then? Alrighty. So here we ran the experiment multiple times, and if you look, you have concentration A and you have concentration B. A goes from 0.1 to 0.2, then it holds steady at 0.3 for the last 3. B holds steady from 0.1 for the first 3 and changes with the last 2. So what you want to do is you want to look at each individually. So let's look at concentration A first. We want to identify when concentration A changes, but concentration B holds the same. So A changes between experiment 1 and 2. B is held constant, so I can use that. So if I'm looking at concentration A, okay, it goes from 0.1 to 0.2, so we're doubling it. So now I want to see how that affects the rate. So I'm going to take 4.0 times 10 to the negative 4 and divide that by 2.0 times 10 to the negative 4. And that's going to be 2. So if we're doubling the concentration of A and we doubled the rate, that gives us an order of 1. Let's look at when B is held constant. So here in experiment 3 and 4, B is is changing, and A is held constant. We don't want to use 4 and 5 because going from 0.2 to 0.3, that is not a consistent change, mathematically speaking, so I wouldn't do that. All right, so if we're looking at concentration B, we're going from 0.1 to 0.2, so we are doubling that concentration. Going over to the initial rate, so I'm going to take 2.4 times 10 to the negative 3 divided by 6.0 times 10 to the negative 4. When you go through and you do that, you get 4. So if you double the concentration, the rate quadruples. Therefore, that has a squared effect, so your order is 2. Now, write your rate law. So rate equals K times the concentration of A, it's the first order, so I don't have to write anything, times the concentration of B squared. The overall order is a third order reaction. Now, you could theoretically solve for K, right? It does not matter because we're not changing the temperature here. Therefore, you could use any one of these experiments, right? So if we use experiment 1, you could have 2.0 times 10 to the negative 4 equals K times the concentration of 0.1 times the concentration of 0.1 squared, right? And you could go through and solve for K. So give that a shot and see if you can figure out. And remember, it's a third order reaction, so you can figure out the units as well.